A humongous machine in Germany has just turned on a furnace hotter than the sun, capturing fusion in a magnetic bottle for nearly half a minute. It's not science fiction, it's the cutting edge of real-world clean energy. This isn't just another science milestone. Fusion power, the same force that lights up stars, has been humanity's energy grail for decades. The key lies in sustaining hot, dense plasma long enough to unleash more energy than we invest. Until today, fusion reactors keep falling short. But now, a Stellarator in Greifswald, Germany, is rewriting those limits, and it might finally light the way to limitless carbon-free power. In early June 2025, the Max Planck Institute for Plasma Physics, IPP, announced that their Wendelstein 7X Stellarator in Greifswald, Germany, shattered previous fusion records, elevating the triple product to tokamak levels during long plasma pulses. That triple product, plasma density x temperature x confinement time, is a crucial metric defined by the Lawson criterion. Only once this number is high enough will a reactor start producing net energy. This is no small feat. In nuclear fusion, reaching the right balance of these three conditions is like tuning a musical trio where each instrument is made of fire. Too dense and plasma disrupts. Too hot and it destabilizes. Too brief and energy leaks away. Achieving all three for longer durations is what physicists have pursued since the 1950s. Unlike tokamaks, which rely on internal plasma current, Stellarators trap plasma using complex external magnetic coils. That stability is vital for long-term operation, something tokamaks struggle with. Wendelstein 7X began operations in 2015 after over a decade of painstaking coil calibration. Its twisted magnetic field lines are so complex, they were only made possible with supercomputers capable of modeling four-dimensional geometry. These coils must be wound with sub-millimeter precision. A misalignment of even a few millimeters could mean plasma drifts off course, crashing into the chamber walls. That's why the design of W7X is often considered one of the most intricate engineering challenges in modern physics. Even the name Stellarator comes from its star-like plasma behavior, reflecting its origin in fusion concepts first proposed by physicist Lyman Spitzer in the 1950s. But those early prototypes were plagued by energy loss and limited control. Wendelstein 7X is the culmination of more than 60 years of iteration, an embodiment of fusion's long, winding path from dream to possibility. This latest experiment was part of its second operational phase, after extensive upgrades in 2022. Much of the groundwork, cooling diverts, tuning its magnetic cage, and scaling up heating systems, was completed in February 2023. The team also replaced graphite tiles on the inner wall with water-cooled metal components, allowing much longer runs without overheating. German funding, 80%, and EU support, 20%, brought the total project investment past €1 billion, making it one of Europe's largest energy science ventures. Leading this breakthrough were Thomas Klinger, head of operations at Wendelstein 7X and head of Stellarator Dynamics at IPP, and Robert Wolf, head of Stellarator Heating and Optimization. Their team combined continuous fuel injection and pulsed microwave heating, launching 90 frozen hydrogen pellets over 43 seconds into a plasma heated to 30 million degrees C. Each pellet, no bigger than a grain of rice, was accelerated into the core like ammunition from a railgun, feeding the fusion flame. Picture this: 90 tiny frozen hydrogen pellets, each shot at 8,600 miles per hour, coursing into a seething plasma chamber. The pellets burn like a star within a bottle. Coordinated microwave pulses ignite the plasma, jostling electrons and ions until they whip past 30 million degrees C. It's a cosmic dance inside a machine the size of a small building. That precise choreography extended plasma confinement enough to set a new energy turnover record. 1.8 gigajoules over 6 minutes, surpassing the previous 1.3 gigajoules from February 2023. Even China's East Tokamak, often called the artificial sun, couldn't beat it earlier this year. To put that in perspective, 1.8 gigajoules is roughly the energy needed to power an average European home for about 15 days, released in just 6 minutes. In fusion research, that's colossal. W7X wasn't always destined to succeed. Early test runs were plagued with uneven heating and insufficient fuel retention. Engineers had to meticulously refine the heating profiles, redesign pellet injectors, and recalibrate the magnetic coils. Success came only after years of iteration and failure. The breakthrough wasn't simply technical, it was cultural. Hundreds of physicists, engineers, and technicians across Europe contributed to this coordinated dance of magnets and microwaves. Behind each second of plasma was a year of preparation. Behind each stable reaction, a mountain of simulation, diagnostics, and design. When asked about this milestone, Klinger said, "The new record is a tremendous achievement by the international team, marks another important milestone on the way toward a power plant-capable Stellarator." Wolf added, "Much more than mere numbers. They represent a significant step forward through outstanding international collaboration." These are not empty words. The ramp-up of W7X from brief pulses to minute long runs shows you can add fuel while maintaining stability, one of the most stubborn engineering challenges in fusion. Before this, tokamaks like JET in the UK and JT60U in Japan held the record, but only for fleeting bursts and without the safety of external magnetic coils. Stellarators, by design, are inherently stable and could run indefinitely, making them uniquely suited to become the backbone of future power grids. Researchers had long feared Stellarators were too complex to ever become practical. But with advancements in machine learning and magnet design, W7X has changed that narrative. Its successful operations signal that precision-built Stellarators can overcome earlier limitations and might even surpass tokamaks in long-term feasibility. One of the most promising outcomes is not just the stability, but the predictability. Stellarators produce far fewer instabilities, which means far less chance of catastrophic disruption. That makes them safer, easier to automate, and possibly cheaper to maintain in the long run. Yet even with these breakthroughs, there's more to do. Reaching net energy gain, where a plant produces more electricity than it consumes, still requires pushing the triple product higher. ITER, a giant tokamak under construction in France, aims to eclipse that threshold by the late 2030s, but it may face issues with pulsed operation and plasma instabilities. Stellarators like W7X may offer a cleaner, steadier route, less prone to dangerous surges or current disruptions. What does this mean for our energy future? W7X isn't powering the grid, but it's turning fusion theory into engineering reality. Long-term stable plasma means reactors could one day run for hours or days continuously, rather than pulsing on and off like a mechanical heartbeat. The implications are vast. A global power source that's carbon-free, fueled by hydrogen isotopes found in seawater, and producing minimal radioactive waste. It would offer humanity a clean energy solution not just for a century, but for millennia. As Farhat Beg and George Tynan from UC San Diego noted in January 2025, the hurdle is now engineering. Materials that can withstand neutron bombardment, fuel cycles tapping lithium to breed tritium, and reactor walls that survive extreme heat. Solving those problems isn't fantasy, it's ongoing. ITER will test many engineering systems at scale. Meanwhile, private fusion startups are popping up with compact devices, exploring both magnetic and laser-based systems. Some are aiming for hybrid approaches, combining magnetic fields with advanced AI diagnostics to self-correct plasma disruptions in real time. The W7X team's success doesn't just improve Germany's standing, it inspires engineers and nations worldwide. The global fusion ecosystem, led by projects in France, China, the US, Japan, and South Korea, is charging ahead with faster technology cycles, new materials, and smarter control systems. Even NASA has shown interest in adapting fusion concepts for deep space propulsion. Still, hurdles remain. Reactor walls erode, magnets need cooling, fuel recycling systems must scale, and all without collapsing under their own complexity or cost. Yet the story has shifted. Fusion isn't a distant dream, it's a sprint underway. With each breakthrough, we edge closer to the moment where humanity might control the very power that fuels the stars. Germany's breakthrough at Wendelstein 7X has smashed fusion limits and injected fresh hope into the clean energy race. Stretching plasma stability from seconds to nearly a minute isn't incremental, it's transformational. If Stellarators can scale further, they might rewrite how we power our planet. This is science at its most powerful. Plasma dancing at stellar temperatures, human ingenuity shaping the future of energy. If you're as fascinated as I am about how this gas bottle in Germany may soon flood our world with clean power, hit subscribe now. We'll keep unpacking the next big leaps in fusion, space, biotech, AI, and more. What do you think? Could a fusion plant be powering your home within our lifetimes? Leave a comment and let us know. And don't miss our next video on how private fusion startups in the US are racing toward break-even. Subscribe for real recent science discoveries delivered weekly with the passion of explorers and the rigor of researchers. Until next time, keep wondering.